Assalamu alaikum warahmatullahi wabarakatuh everyone. Today inshallah we will solve problem 19 from chapter 3, and the question says, referring to the spring loaded inverted pendulum system shown in figure 32, obtain the natural frequency omega n of the system using the energy method that equates the maximum kinetic energy and the maximum potential energy Umax. Choose the potential energy at the equilibrium state to be zero. So at this state, and this is how the mathematical model of our system should look like. Okay, but we will derive it inshallah today. Now, I will not use actually the U max equal T max, or the kinetic or the maximum kinetic energy equal the maximum potential energy. I will use the normal method, which says that the derivative of the energy with respect to time equal zero. Okay, so first we need to identify what is the kinetic energy and what is the potential energy, right? So there is two forms of kinetic energy. There is translational and torsional. For the translational, which is in x, y, z direction, and the torsional in theta direction, its equation will equal to mx square, mx dot square, and for the torsional it will be half j theta dot square. For the potential, or U, it will have the potential of our mass, which is mjh simply, and it will have the spring potential energy. And there is two types of potential energy for the spring. There is the translational and the torsional. For the translational, it will be half k x square y square z square. It depends on the name of your degree of freedom. And for the torsional, it will be simply half k theta square. Okay, now let's first find our kinetic energy equation, and it will be just for the torsional part, which is half j theta square. And for the potential, we will have a bit different equation. We have the spring, right? So we will have 2 multiplied by half k theta square. And the reason why I wrote here 2, because both springs are equal, or have equal constant, or spring constant. And the other thing, they deform the same. Okay, so if this is call it x, okay, and we have our spring here and we have our spring here. If this is shrinked by x, okay, this as well will extend by x, right? So we can say that they are the same and we can sum them up. Okay, and also we have our potential energy from our mass. Now, we said previously whether to consider the mass or not. And the way of determining whether to consider our mass or not in the equation of motion that we derive is by seeing the mass, how it will affect our springs and dampers in its equilibrium position. If, for example, if I remove the mass, is there anything going to happen to the springs? Are they going to stretch or unstretch? In this example, they will not, because at the equilibrium position, if I remove the mass, nothing will happen to the two springs. So in that scenario, I will include the mass in my energy of equation. Okay, so it is mgh But what is that h? Okay, to know this h, we need to draw our mass at the equilibrium position with the rod and at the displacement position, let's call it. Okay, now this is we know what it is, L, right? And this is as well L after some time, after theta. Okay, now this distance from here to here is what? Is L cosine theta, right? So this distance must be L minus L cosine theta, which is our h, right? Because our mass moved from this position to this position, which is the h. So our h will be L minus L cosine theta. Okay, all right. Now let's write our h. It is L minus L cosine theta. Sine theta. And for the sake of consistency, we will go with the theta coordinate. So we will eliminate anything that is related to the x coordinate. Okay? Sorry, this should be not theta, this should be x squared because we are moving in, or we are the spring displacing in x direction, not theta direction. Okay? Okay. So this is going to equal to half ml square theta dot square, because j for the pendulum will equal to ml square, right? And before doing anything, there is a small mistake here. This should be minus, and the reason why, because our mass here transferred from this position, which is the datum or the equilibrium position, to this position. Okay, so if your mass transferred from the datum to a position below the datum, h should equal to a negative value. Okay, just to clarify everything here. Now let's continue. Okay, so we need to transfer from theta or from x to theta, and to do that we will draw our beautiful triangle, and that's it. Okay, this is our equilibrium position, and this is our half rod, and this is the distance x. Okay, and this is theta. Okay, I will put h here. Now if you see the figure here, h should be in this side, right? But you need to be careful because our body of interest is not this, it is the road itself. So the road was h at equilibrium, or half of the road was h at at the equilibrium position, but now after a rotation of theta, h transferred to here. Okay, so sine theta will equal to h, and we know that for sine theta, for small angle, it will be just theta. So this is theta x over h. Okay, and also for cosine theta, it will be, for small angle it will be 1, but I will not do that here, because if I did it, it will be L minus L, which will make this term go to 0, and we don't want that. So I will convert my cosine function later. Okay, and let's plug theta here, or x. So x will equal theta h. Okay, so for this term, it will be k h square theta square minus m g g l 1 minus cosine theta. Okay, now I will take the derivative of this part first. Okay, or the kinetic energy equation. Half half I will take the derivative with respect to time, so half ml dot multiply by 2, so this will go, and this is double dot. And how we got this form dt, it is like theta dot multiplied by theta dot, right? So the derivative of that using the product rule or the chain rule, because theta dot, we don't know the function exactly. What is the function theta dot? So I will take the derivative of the first multiplied by the second plus this the first multiplied by the derivative of the second, and sum these two up, we will get this. So this is how we got this term. Okay, okay, this is for the kinetic energy. For the potential energy, we have k h square theta, or 2k h square theta dot, or theta multiplied by theta dot. The same goes for theta as we did before. And for mgl, this term will go to 0 because mgl multiplied by 1 is just a constant, and the derivative of a constant with respect to time is just 0. Okay, and for this one, it will be plus or minus mgl sign, right? So minus multiplied by minus is plus, multiplied by minus is minus. So this will be mgl sine theta, and we can convert theta to or sine theta to theta here. Okay, this will equal to 0. Now I will take, oh sorry, it should be sine theta multiply by theta, because also we have function here inside, which is the theta. Theta is not just a constant, it's a function. So we need to take the derivative of that function that is inside the sine. Okay, so this one will go to theta as we said before. Okay, equal to 0. Now taking theta dot as a common factor, okay, theta minus m g l theta equal 0. And we know for sure that theta dot can't be 0, so this term is equal to 0. Okay, so this term is equal to 0, and for omega equal to n, it will be the square root of this term plus this term over this one, right? Because this will convert it to, or let me convert it first, ml theta double dot plus 2k h square minus mgl all multiplied by theta. This is our equation. Okay, so omega n will equal to 2kh square minus mgl, oh sorry, this should be square here, square here. So ml square, and we can simplify it to be 2 over kh square ml square minus g over l. Okay, this is our natural frequency. Thank you guys for watching, and good luck.